Alright, okay, so in this assignment, I'm basically going to go through all these requirements. So it involves creating a signal, modifying the signal, and then filtering the signal. So in these first few parts, I'll be creating my signal. And to start off by creating the signal, I'm going to create a recording. So to do that, will use sound recorder. And I'm going to say my name. So my name is Seb Coleman. Okay. And now, so I'm just going to rename this to Seb's recording or Seb's name. And then once I've done this, I'm now going to just import this file. So I'm just going to find this shown folder, and I'm going to just put it in my MATLAB folder, which is this video assignment. And okay, so now that we've done that, I can now load the Seb's name audio file into MATLAB. So to start this, I'm going to I'm going to use the audio read function, and this takes two values. So the sampling frequency, fs, and it'll store the samples in IP. So now I'll just use audio read, and then Seb's name. .wav. Okay. So now when I load this, we'll see that we get a two column matrix, and sampling is at 48,000. It can either be at 44,100 or 48,000, depends. So now I'm going to play it back by using this sound function, so sound, and then IP and fs, the sampling frequency, and you should be able to hear my name. My name is Seb Coleman. All right, so in part 1 and 2, we read in our signal, and then we got our vector IP and our sampling frequency fs, and then we played the sound back using the sound function. So now what we want to do in part 3 is plot the speech signal in the time domain in seconds. So basically, to start off this, we need to first extract the first row vector, because if we just look into our variable IP, you can see that it's a two column matrix, and we just want the one. So if we do this, we'll say, so we want all the rows, and then we want just the first column. So that's how we define just the first column. And now what we want to do is put this in bins. So bins is just a placeholder for MATLAB. So what we're going to do here is we're going to say we want the number. So bins is the samples here. So we want the bins start from 0 and then to the length of x, or IP, sorry, -1. So basically what this is doing is it's saying that we want to start from 0 because in MATLAB it always starts from 1, so we have to define 0, and then we have to take 1 away from the length to keep it the same size matrix. So next, we want to put this into time. So we'll say t is equal to the bins, and then we want to divide this by the sampling frequency, so fs. And the reason why we do this is, remember that bins are our samples, and we want to get it in seconds. The sampling frequency is hertz, which is the sampling frequency is samples per second. So if we divide the samples by samples per second, we'll be left with our seconds. And finally, let's plot it. So plot t on the x-axis, IP on the y-axis, and then we want our labels. So x label, we're going to say amplitude. Y label, we're going to say we want we want, on the x-axis we want the time, so time in seconds. and then the Y label we want amplitude, and then we'll put in a title as well. So title, and we want speech signal. And hopefully, if we plot this, we'll get what we bins. 0 length. I just spelled length wrong. Yeah. Okay, so we'll run it again. And here you see that our time is in seconds, 3 seconds. The speech was, and so for part 4 and 5, we're going to start by copying this code that I have in the bullet points here. So this is the base cutoff frequency with added randomness to it, and same with the tone frequency. And we are then going to synthesize our high frequency noise and tone frequencies with using these variables, and we're then going to add the noise to our signal. So we'll start now. So I'm going to copy and paste the tone frequency in. I'm then going to copy and paste the noise cutoff. And so now that I've done this, I'm going to run it and just show, so we can see our noise cutoff here is 20,845 hertz and 2,802 hertz. Okay, so now I'm going to create the noise signal that I want. So my noise, or cutoff, or sorry, actually, we'll just call it the noise. Sorry, noise signal. And noise, we're going to create a random signal using rand n, so random number, so random number sequence with the size of IP. So it's going to basically just generate a load of random numbers with the same length as IP. So now that we've created the random noise signal, we now want to create a signal that only has high frequency noise in it. So to do this, we're just going to use the butter function. So basically how the butter function will work is that we're going to use this butter function here, and it's going to take the order we want. So it's going to be 6, which means it's going to have a slope of 120 decibels per decade. So it's quite a steep slope. And we're just going to take the high frequency noises, which means high pass filter. We also need to put in our frequency, and the frequency has to be normalized. So to do this, we're going to take the noise underscore cutoff and divide that by fs over 2. And then we're going to say it's high, and this will generate a high pass filter with the specified normalized frequency here. And now we just want to create the noise signal again. So we're just going to use the same variable and filter using the B and A coefficients we defined in the previous function. And then we're going to put in the noise as our signal. So we're taking this signal, putting it in here, and then taking the B and A coefficients, which is our filter, from our requirements in the parameters here. Okay, so this is our noise signal. Next, we want to create the tone. So the tone is going to be equal. We're just going to call it tone, and it's just going to be a sinusoid. It's 0.1 amplitude cos, and then 2 times pi times our tone frequency, so which is 1536. And then we're going to multiply that by t to put it into a vector. Now, what we'll see here is that this tone vector is a row vector. We want it to be a column so we can add it to our signal. So to do that, we just we just want to transpose the matrix. So we can just basically put our signal in. So our sig is equal to IP plus noise plus tone, but we want to transpose the matrix, and we just do that with a whatever that's called. Okay, and we'll just run this, and we will have our new signal. So sig is here, and we can just plot that to show what we've created. So we'll say if I just take this code here and copy that and bring it down here, and then just do sig, and we'll see what we've created. So yeah, you can see that we've completely distorted our signal, and there's not much you can really see of it left. So my name is Seb Coleman. Okay, so part 6. So for part 6, we're going to create a second order filter. So we'll just go back to the requirements. So our second order filter, using the butter function with a cutoff frequency set equal to half the noise or cutoff frequency. So just to do this is easy. We're going to use the butter function again. So we use B and then A, and then we're going to use, so we're going to equal that to the butter function, so butter, and then we need to put in our order, so which is going to be 2, and then our cutoff frequency. So we're going to use the noise underscore cutoff, and then divide that by 2, and then use the sampling frequency divided by 2 just to normalize it again. So divide this by 2. Okay, so and then we want it low, so just low pass. Okay, so we've created the B and A coefficient here. Okay, so in part 7 and 8, we're going to draw the signal flow diagram. We're then going to draw the difference, or we're then going to find the difference equation. And using this, we're then going to find the first 3 outputs of our system. And the signal flow diagram is of this filter we created. So we're going to use these B and A coefficients. So starting off, first find the B and A coefficients by just type B A here, so from our variables we created earlier. I'm just going to take a screenshot of this, and then we're going to trans over to a screen. There we go. Okay, so I'm just going to put this up, and then I'm going to go over to Zoom. Okay, so all right, so starting off, we can just have our input x of n, and this is going to have a multiplier, and it's going to have an adder. Okay, and that's going to be our output y then. Okay, so now our first is 0.2106. Right here. And then we have a delay, so we're going to put a delay here. And we're going to have another multiplier, so here and then right there, and that will be 0.4211. Now our next delay, the B and A, so there's the B coefficients that are come on the left side here. And that is going to be 0.2106. Okay, so now we're going to start with the A coefficients. So we have a delay here, first delay, our first delay is 0.3512. And then the second delay is going to be negative 0.1935. Okay, so we've created our signal flow diagram here, and now we can create our difference equation. So our difference equation will be y of n is equal to 0.2106 x of n plus 0.4211 x of n minus 1 plus 0.2106 x of n minus 2, and then plus 0.3512 y of n minus 1, and then minus 0.1935 minus 2. Okay, as far as C, let's just see if you can zoom in here. That's our difference equation. Okay, so now we can calculate the first three outputs. So our first three inputs we can find on MATLAB. So we'll just do that. And that is done by, so we can get sig 1 to 3. Like so, and here are our first three inputs. So I'll just I'm just gonna screenshot these again. Okay, and then let's go open back Zoom. Okay, so we can say that x of 0 is equal to 0.1, x of 1 is equal to 0.098, and x of 2 is equal to 0.709, or 0.0709. Right, and now we can find our first three outputs using the difference equation and these inputs. So the first input is going to be y of 0, which is equal to 0.2106 times 0.1. And that is going to equal, get it up here on MATLAB. So that will be 0.2106 times 0.1. Well, 0.02106, 0.211. Okay, and then y1 is going to equal it's going to equal 0.2106 times 0.0938 plus 0.4211 times 0.1 plus 0.3512 times 0.0211. Okay, and if you just look at this as y of n minus 1, this is the last output we had, which is 0.021. And then this is our second, this is n minus 1, this is n minus 1 again. So we get 0.1 our first input, and this is our second input. And then if we put this into MATLAB, we should get, so we'll just put this into MATLAB, so 0.2106 times 2106 times 0.0938 plus 0.4211 times 0.1 plus 0.3512 times 0.0211. We get 0.093. So y of 2 now is going to equal, go back, y of 2 is going to equal 0.2106 x of n, which is 0.0709, and then plus 0.4211 times x of n minus 1, which is 0.0938, and then plus n minus 2, because we can now do that, 0.2106 times 0.1. And now plus from our y's, we get 0.3512, and then y of n minus 1, which is 0.0693. Ready fit in there, and then minus our last one, which is 0.3512. Sorry, let's put that in here. 0.1935, and then y of n minus 2, which is 0.021211, and that will give us. Okay, so I've typed the result here, and we have 0.0957. So if we now we can now use the filter function to confirm this. So our signal is sig, and we want to just have 3 first inputs. So this should show us something similar to what we've calculated. So here's our first 0.0211, and then our second 0.0693, and then our third 0.957 or 0.0957. Okay, so part 10 of this assignment requires us to design a minimum order filter. We want to reduce the noise by 60 dB, so that means we want to reduce everything for our noise cutoff, which is over here, defined here. And then we want a 3 dB passband ripple and the passband from 0 Hz to fs over 4. Okay, so just to start off, I want to define the norm equals fs over 2 instead of drawing fs over 2 every time. Then I'm going to use the Baudard function. So the Baudard function takes 2 outputs, n and omega c. So n is the order that this function will recommend, and omega c is the cutoff frequency. So these are just both outputs of this Baudard function. Okay, so Baudard, and then I want to do fs over 4 divided by the norm, put it back to the normalized frequency, and then again want the stop band. So it'll take 4 parameters: the passband ripple, the passband frequencies and stop band frequencies, and then the ripple and the attenuation. So I don't want to put in the stop band, so the stop bands are cutoff frequency. So we're just going to say noise underscore cutoff divided by fs, or divided by norm. And then I want to put in 3 dB and then 60 dB here. And then this should I'll actually take this off just to show what it'll recommend. So when I run this, we'll see that so the minimum order is 6, and this is the recommended cutoff frequency in normalized. And then I now want to put this into a butters function, so b and a, and then equals butter. And then my recommended n and omega c, so my cutoff and my order. And then I want to make it low because I want to get rid of the high frequencies. Okay, and now I just want to make sure that I've done this, so I'm going to make a new, so I'm going to call it sig filter 1 is equal to filter b, and we're using sig. Okay, so just to make sure this is working, I just want to use, so we'll do freak said b, said b a, and so I'll just show you the frequency. So here we can see, so basically what I'm looking for is, so I'll need to put this into the normal, so 19,000, so 19,436 divided by 24,000, which is fs over 2. So we're 0.8098, so at that point it should be minus 60 dB. And we should see that, so yeah, around, yeah. So we just seen that there, we're happy enough. Okay, so now that we've designed that, I just we'll plot the magnitude plot just to show that we've gotten rid of our noise. So plot ABS FFT of a sig. So this is what it was before. Sig. So we should get our plot. There we go. Right there. Okay, so this is the noise here we're trying to get rid of, and if I plot the absolute of FT of sig of sig filter 1, there. So you can see we've gotten rid of the noise here. Now we just need to get rid of the tone. So to do this, I'm going to go ahead and use the butter function again, but this time we need to use a stop band because we are trying to get rid of this here, the tone at this frequency. Okay, so to do this, we're going to use a stop band, and basically we need to define our pass band and stop band areas. So the pass band, I'm just going to go ahead and say equals 0.01 because we can't start from 0, and then 23,999, and then stop band, which will equal to we want to equal this to be the tone frequency. I'm going to say minus 10 hertz, and then tone to plus 10 hertz. And we need to divide this by the norm. Then we need to use the buttord function again. So n1 omega 1 is equal to buttord. And then I'm going to just put in PB, so pass band, stop band, and I'm just going to give it the ripple of 4 again, and then say I want to reduce by at least 40. Okay, so we've done this, and now we've done that, we can put this into the butter function. So b1 a1 again is equal to butter n1 omega 1, and then we want a stop. Okay, and now that we've done this, we can just make sure that B, A1 are filtering what we want. So just show these requirements are being set. Okay, so this is our stop band. Okay, so first of all, I just need to make sure that, so it's 2807 divided by half our sampling rate, 0.117. So we just zoom in here. Oops. Yeah, so we can safely say that that's been obtained by that much. And then we can use the Z plane to make sure that the system is stable. So we'll just say B1, A1, and we'll just run this. And our system is stable. We could try increase the order to make a more selective stop band, or we could decrease the range of frequency. So let's just do 5 here, and we'll be able to see that it gets closer. We can see that it got a lot closer here. So if any of these poles go outside the circle, it'll be unstable. So this system is stable. All right. So next, I'm going to plot. I actually just want to show that we have now, so we're now going to combine the signals. So I'm going to just call this sig filter 2. Oops. Sig filter 2. And then I'm going to let that equal to filter filter B1, A1, and then sig filter 1. Okay. Okay, so that's sig filter 1, and then I just want to just plot the sig filter 2. Actually, I'll just do it down here real quick. FFT sig filter 2, 3, and then just I don't think I've run this. Just run that. I didn't mean to do that. Okay, there. We should see a plot. Let me just maybe get rid of these. Okay, so we see that we've just gotten rid of the tone and the noise, and now we can combine these. Um, so we've combined them here just above here, sig filter 2, and we use the input of sig filter 1, that signal into the new filter. So that probably should be here. And now we just want to plot it. So we just need to make a frequency axis first. So we call freq axis equals, and then I've made the variable bin, so I just need to just divide it by IP length of IP, and then multiply it by fs, which should give me the length. And then I can just plot freq axis ABS of signal filter 2, and then plot. Actually, maybe I should do sig filter. Just do the sig one first. Okay, and then we'll just copy this. B from filter 2, x label, frequency hertz, y label, magnitude, and then okay, so I'll just run this. So this is our original signal, and this is, so the blue is the original and the orange is what we are left with. My name is Seb Coleman. Part 13, we will be doing identifying the low component, frequency components that will produce a significant phase shift. So we're looking for at least a 45-degree phase shift. We're going to pass a sinusoid that we created with the frequency at 45 degrees with respect to the first filter that we designed in part 10 or 11. And we're going to just ensure that our predictions are correct. So we'll start with the freq z function, then the b and a coefficients should stay the same. Alright, and then we want a 45 degrees. So around 0.117. So 0.117 times fs over 2, we're just getting it back into hertz here. So 2808 hertz. Then we're going to create a new sinusoid called sin 2 times pi times our answer times t, and then we're going to pass this sinusoid through our filter. So new sin is equal to filter b a, filter b a, and sin, and then we are going to plot. So I'm just going to close all to make sure that all the figures are closed, and then going to plot sin. Hold on. Plot new sin. And then we can look at our plot we've generated, and we can confirm that it will be 45 degrees. Okay, so I'm going to pick a few data points here. So I'm going to take this point, this point and this point. Okay, so I'm going to calculate, so we're just going to minimize this. What's that? These numbers. Okay, so first I'm going to say Newton, so I'm going to just calculate the degrees. So I'm going to say 955 95507 minus 95505 divided by 95490 plus 9550. Okay, right, so we'll get this answer, and then 360 times this answer give us sorry, no, back to this. I accidentally need to make this negative. It's negative. Here we go. So make this negative, and then 360 times this answer. Yeah, so around 45 degrees.